Now let's suppose that we have a case, and I've kind of set this up like a spreadsheet with an F column, a G column, and a 2-row and a 3-row. We've got a bunch of data. We've calculated a mean of 3.7 for men and a mean of 6.2 for women. Men have a standard deviation of 4, women a standard deviation of 10. Now, given this mean and standard deviation, and if we also have the information that there are 400 men reporting and 600 women, we can calculate the standard deviation that we would expect for these means. And the standard deviation is just going to be this standard deviation for, just what we get when we do the standard deviation for the column of numbers reported for the men divided by the square root of the number of men. So that's going to be 4 divided by the square root of 400, and that's easily calculated. That's going to be 4 over 20, or 0.2. And we can do the same for the women. Okay, it's going to be 10 over the square root of 600. Square root of 600 is about 24.5. Let's just say 25. If we divide 10 by 25, we get 0.4. Now it's actually a little more than that, but let's just round the number off to 0.4. Okay, so now this is a standard deviation we would expect for the mean. In other words, if we repeated this experiment, okay, and asked the men again to report the number of bad hair days in a different month, they would tend to have a standard deviation of 0.2 in their month-to-month results. So this is a measure of how much flexibility there is in this 3.7, and this a measure of how much kind of flexibility or how much uncertainty there is in that 6.2. Well, now, just as we did down here, we can calculate a lower confidence interval and an upper confidence interval, because that's actually what we have here. Okay, the lower confidence interval would be 1.96 of these deviations less than 3.7. Remember, 1.96 is just a Z number that gives you 2.5% above or 2.5% below on the left. Okay, so what we need to do is we want to first calculate how far we've got to go to get Z equals 1.96 for each of these. Okay, we don't have to do that. We can do it all in one calculation. We could do it all in one big formula, especially if we had the right formula, but that's kind of ridiculous. We want to think through what these things mean so we have a better feel for our interpretation of the data. Okay, well, so what we want to do is we want to calculate 1.96 standard deviations, I'll just abbreviate that SD, of our mean. Okay, well, that's going to be 1.96 times 0.2. So that'll be 1.96 times 0.2, which is going to be what? 0.392. I just round that off as 0.39. And similarly for the 0.4. Okay, 1.96 times 0.4, 0.4 being the standard deviation here. So if we want 1.96 standard deviations, we've got to multiply by 0.4. What do we get? We get about 0.78. Okay, now what do we do now? Well, if we subtract this from 0.2, we get the lower end of our confidence interval. If we add this to 0.2, we get the upper end of our confidence interval. Of course, the numbers are different here than they are up here, and I just said that wrong. If we subtract this from our mean, 3.7, we're going to get the lower end of our confidence interval. We're subtracting the 1.96 standard deviations from our mean. Or added to the mean, we get the upper end of our confidence interval. So that gives us, for the lower end, 3.7 minus 0.39 is 3.31. I don't have room to write out the calculation there. I'll kind of write it in a minute. And the upper end of our confidence interval is 3.7 plus 0.39, which is going to be 4.09. Here, 6.2 minus 0.78 is 5.42. And 6.2 plus 0.78 is 6.98. Now I'm going to label a couple of things here off camera so you don't have to sit and watch me label. Okay, I've just indicated that 3.7 plus or minus your 0.39, your 1.96 standard deviations from the mean, which would correspond to this number and this number, but with this distribution, gives you either 0.409 with the plus or 3.31 with the minus, if I've done my arithmetic correctly, and you can easily check me on that. And similarly, the 6.2 plus or minus 0.78 gives us with the plus the 6.98, with the minus the 5.42. So this would be the lower and upper confidence intervals at 95%, and maybe I should put 95% there. Now remember, the relation of the 95% is that z equals 1.96 gives you 2.5% on this side, 2.5% on this side, leaving you 95% in between. So you have your lower and upper confidence intervals on both of these. Now let's do just a little bit of interpretation on that and talk about where the interpretation might lead. Okay, here I've begun to sketch. Here's the 3.7 on one axis. Here's the 6.2 on another axis. 6.2 should actually be a little further out this way, but I didn't leave myself room. This would represent the distribution for the men, and this 0.39 is your 1.96 times the standard deviation of the mean. And excuse me, on this side and this side of the 3.7, you have your 95% confidence interval. It's like this picture. This would be the 3.9 on one side, the 3.9 on the other side. Of course, the numbers are different here. So your picture is going to look very much like this. With only about 5% of your area outside of here and here. Over here, your distribution is going to look very similar. It's going to be broader because you've got a bigger standard deviation of the mean, and if you multiply it by 1.96, you get a bigger number. So you would have a distribution that might look more like this. But we see that this distribution has almost no overlap with this distribution. So there's almost no overlap. I'm going to write a couple of things. Okay, there's almost no overlap between these distributions. This distribution tails off to practically nothing about here. This one trails off to practically nothing about here. Between here and here, and this one really should be further to the right, so that null region ought to be even wider. There's really only an infinitesimal chance that this mean could actually be anything but less than this mean. So we said there's very little chance that the actual mean for men isn't less than the actual mean for women. And the conclusion then would be that women have more bad hair days than men. Okay? Well, these days women tend to have longer hair than men. That's not always the case, but that's the tendency. So, longer hair might be more susceptible to bad hair days. Also, there might be differences in judgment. Men might not care as much as women, although they might well, they just don't want to show it. Okay, well, all kinds of possibilities here.